All right, let's jump back into it. Trigonometric identities. We got a lot of these things, and we have seen a lot of them, and you will be tested on a lot of them. So you need to spend some time making sure you're familiar with the different trigonometric identities as they keep coming up. Now, I'm not talking about some really crazy ones. I'm talking about the ones that, the kind of the basis that we're using for other identities. And again, the first ones you really got to know is you got to know what happens with the relationships with sine, cosine, tangent, cosecant, secant, and cotangent in terms of the right triangle. It seems like the right thing to do, right, to start off with. And that's how we started off at the very beginning of the term. We had some kind of triangle, we had theta, and then we had what's called the opposite side. I'll just call it A, and then B, and then C. Because opposite side is really a relative term. Opposite to what? Well, to this angle. And if I'm talking about this angle, then that's the opposite side. But anyways, we started off, we said sine theta is going to correspond to A over C, and cosine theta is going to correspond to B over C. And then if you take the ratio of the two, you get tangent. And one of the things we also discussed is tangent. You can think about it as being slope of a tangent line, maybe slope of a line that goes to the origin. We see that, where this corresponds to rise over run. So I can think about from that vantage point if I put it over here on an xy axis. I can see that. And then we also have the reciprocal identities that we got to know, the secant, cosecant, cotangent we keep talking about over and over. And we do see the Pythagorean theorem here. It's a right triangle. So we have a squared plus b squared equals c squared. But again, it's a trig class. It's not like a high school geometry class. So we take it a little to the next level. You can take everything here, maybe solve for a, solve for b, drop it into the Pythagorean theorem, and that led us to sine squared theta plus cosine squared theta. And then off of this, we said, okay, let's be brave and courageous, daring, and divide everything by sine, right? Divide everything by sine squared. So you have sine squared over sine squared, which gets you 1. And then cosine squared over sine squared got you your cotangent, and then 1 over sine squared got you your cosecant. Then you said, well, what if we divide everything by cosine? Okay, well then that will get you sine over cosine, which is going to correspond to tangent. And then cosine over cosine, squared again, that's going to correspond to 1. And then 1 over cosine, it's going to correspond to secant. So we got our 3 different variants of the Pythagorean theorem in terms of our trigonometric functions. And yeah, you guys got to know these right here. They're very, very useful. And especially if you're going to calculus, you really have to know these 3. They're extremely useful. But we didn't stop there. We kept talking about some additional identities. And another one we did talk about was, what if I'm going to have cosine theta plus phi? So we talk about the distortion, the change in the angles. Okay. Well, this is going to correspond then to cosine theta times cosine phi, and you'll have a sine theta sine phi. But because there's a plus sign, we're going to get a minus sign in between. And if I had a minus sign, so I'm looking at the difference of the angles, well, the difference is just going to be that you're taking the addition of it. Okay. So if you have plus or minus, it gets you your minus plus. Okay, just link up accordingly. If you have sine theta plus phi, you're going to get your sine theta cosine phi, and then switch it up. You're going to have cosine, and if this is sine theta, this is going to be cosine theta. And if this is cosine phi, this is going to be sine phi. Okay. Now, if it's plus here, it's plus there. And if it's minus there. Now, these identities, these are very, very useful, especially when I want to start finding values of angles that I'm not quite familiar with. Okay. Here's the problem. I only really know what happens at 30s and 60s and 45s, and it also happens on the axes. That's not what this is at all. So how am I going to figure something out? Well, kind of what we do a lot of times. You link knowledge to other knowledge that you already know. So you want to take this and link it back to 30s and 60s and 45s. So you got pi over 12, and you got to think about how you can take this and break this thing apart and use one of these identities up here. So pi over 12 can be written in a lot of different ways. Addition is not really all that well defined. If I have 5, for instance, I can write 5 in a number of ways. I can say 2 plus 3, I can say 4 plus 1, but I can also say 6 plus minus 1. There's a lot of ways if I can do this. If I'm looking at prime factorizations, integer factorizations like 6, okay, there's kind of a limited number of ways I can do this. There's not as much as I can do with addition. Eventually I get things like 1, 2, and 3, and that's 6. And I'm pretty much locked in place. Okay? But anyways, that does give us a little bit of freedom when I start looking at the decomposition. And you do want to find things which are going to be helpful. Don't look at things which are not going to be helpful. You could take pi over 12, and you can say, well, that's just going to be the same thing as 5 pi minus 4 pi. Because isn't 5 pi minus 4 pi pi? Absolutely. It does work. This does equal that. And you can use properties of fractions and rip this thing apart. You can say this. Again, a lot of times we talk about simplifying fractions, but we can also talk about unsimplifying fractions. If you can combine them, then you can uncombine them. If you can build it, you can break it. If you can tie your shoes, you can untie your shoes. But I can't tie my shoes. Literally, see? Like, Orlando, I got boots. There's no shoelaces here. I love that. I got tired tying my shoes. I got boots. Okay, anyways. Okay, so here, 4 pi over 12, that does get me pi over 3. And I know what happens at pi over 3. I don't got a clue what happens at 5 pi over 12. I can figure it out. But that's what I'm trying to do. I'm trying to figure things out. So it's kind of a big question mark. I want to take this back to something that I know. And what I can do is, once again, I might want to just look at the factors for 12, 3 and 4. What if I said 4 pi minus 3 pi? And I do the exact same thing. I take this and I just rip this thing apart. I'll have 4 pi over 12 minus 3 pi over 12, which then, okay, 4 goes in 12 3 times. 3 goes in 12 4 times. And then I know what's going to happen. See, I'm looking ahead. I'm anticipating what I'm about to do before I decide to invest a lot of time and energy into the calculation. But I do know if I have this difference, I plugged it in, I know what happens at sine pi over 3 and cosine pi over 3 as well as pi over 4. So this tells me that this is probably a good track to go down. Again, it's not necessarily the only way I can work this problem, but it does work. All right, so I just want to take this pi over 12 and I want to rewrite it as pi over 3 minus pi over 4. You're trying to find something that's going to work. Then hit it with your angle difference identity. And notice the difference, again, between these two different identities. When you have cosine, look at the angle sum or the difference. The cosines go together. The sines go together. When you're looking at the sine, you have a sine and a cosine, and you have another one with a sine and a cosine. So I guess it's kind of like when you're going to sin, it's great to be around other people. You know, share the sin. Don't do that, by the way. That's bad. But remember, however you need to, okay? So, drop in pi over 3, pi over 4. Okay, that's great. Fantastic. Okay, so sine at pi over 3 is root 3 over 2. Cosine at pi over 4 is root 2 over 2. Another root 2 over 2. Cosine at pi over 3 is 1/2. And would you look at that again? There's something going on here. The denominators are identical. I wonder what's going on here. Why it keeps popping up like this? There it is. Let's say for the moment, I want to find out what's cosine at pi over 12. I know what happens at sine at pi over 12. I can go through the whole entire process yet again. I could look at pi over 12. I could take this. I can apply the identity, but I don't really have to, but I could do so. The other approach that we could do is, since I know that this is sine at pi over 12, and I know what sine is, opposite over hypotenuse. When I look at the fraction, it's going to be opposite over hypotenuse. I could construct a triangle. The numerator is opposite side. The denominator is the hypotenuse side. And if I want to find cosine, adjacency over hypotenuse. Really what I need to do is find this piece right there. And I'm done. And one approach that we could do, Pythagorean theorem. I can use this. Okay, I can take all this, I can drop it in right here, and then I would solve. And I got to worry a little about, should I take the positive case or the negative case? Because as you know, when you take the square root, it's plus or minus. It's a package deal. Okay, you can do all that. But we do know all two of these pieces over here, just another other piece. We can simply just say, okay, 4 squared, root 6 minus root 2 squared plus b squared. Just take it back to what you would think about in terms of the Pythagorean theorem. And then crunch this out, solve for b, and then you get your cosine. Okay. So it's just another approach of how you can solve this problem. You don't necessarily have to use this identity again. You can use this, and what we're doing is we're just building knowledge upon knowledge, using what you already have and what you already know to find out what you don't know. Okay, but you know, there's a lot of ways you can go about these problems. All right, I want to stop. I want to see if this is resonating, if it's making sense. Suppose you have some kind of measurement. You find out that cosine of theta is going to be 3 over 5. And you also find out that sine of phi is going to be 5 over 13. Here's your mission. What is sine of theta plus phi? And how can I find it? Well, I got this really nifty identity up here. Sine of theta plus phi or sine of theta minus phi. And since the objective is to find this, a really good spot to start is right here. So that's probably the first thing I want to do. Since I want to find this, let's look at it. So there's 4 things I got to find. You find these 4 things, you're done. But 2 of them are given. Right there. So I'll come over here and I'll replace it. And take this and replace it. What am I really asked to find? Those two things. If I can find sine of theta and cosine of phi, I'm done. That's the objective. But how am I ever going to find these values? I only know cosine of theta. And I know sine of phi. But wait a second. I know cosine theta. And the right thing to do is maybe look at a right triangle. Because I know cosine theta, adjacent over hypotenuse. And for sine, it's opposite over hypotenuse. And the objective is really find the sine. Okay, so I can just hit it with the Pythagorean theorem. Call this side A, and we'll call the side over here B. A squared plus 3 squared equals 5 squared. Okay, now, when you're doing your number crunching, you know, you could do things hard, the hard way, or you can try and find things to make it easier. The choice is always yours. You can always make a problem as complicated and as difficult and as hard as you want it to be. I don't recommend it, but you have that choice, you have that freedom, that is your right, you can do so. As for me, what I try to do is I try to do things a little bit easier by looking for patterns to help me out. And the more information you have about a calculation, the more things you can use. You may not use them, but you do have that option to use them. Okay, so solving this, probably what a lot of people are going to do, honestly, they're just going to get into the grind and try to get done as fast as they possibly can. And there's nothing wrong with that, but it can definitely make things a lot more challenging. You know, they might just say, okay, I'm just going to take this, I'm going to square this out, then I got to think about 25 minus 9, and okay, again, nothing wrong here computationally wise, and you would get 16 in the end, and then you would take the square root, but please remember when you take the square root, it is a package deal, plus or minus goes along with it. Okay, now you got to make the choice as to, am I taking the positive case, am I taking the negative case, and how am I going to figure this out? Well, you wouldn't if they didn't give you something like this. Theta and phi are between 0 and 90 degrees. So if you're between 0 and 90 degrees, which quadrant are you in? Quadrant 1. And if you're in quadrant 1, is cosine positive? Is sine positive? Yeah, everything's positive. Okay, so when you take the square root then, you are looking at the principal square root. You are talking about the positive one. Okay, so this would be simply 4. And of course, we could have seen this before because it is our 3, 4, 5 triangle. Okay, now, another way of how you can do this calculation, which can actually be a whole lot easier, is you would have a squared plus 3 squared equals 5 squared. Don't square it out. Take everything, just throw it to the other side. And lo and behold, right before my eyes, I see it. I have 2 squares to which I'm taking the difference of. And when I have 2 squares to which I'm taking the difference of, there is a nice identity known as the amazing hippopotamus property. Still not catching on? Trying. I love that name. Hip hip hooray. Hip hip hooray, God made all of us. Hip hip hooray. Hippopotamus. I have a difference of squares. And for the difference of squares, I know when I have a squared minus b squared, I can take it and re-express it as a minus b, a plus b. 5 minus 3, 5 plus 3. What's 5 minus 3? Kind of late in the day. 2. 5 plus 3 is 8. 16. So that's one way of how I can go at this problem. I can use that, and that can really make things a little bit easier because it's not as big of a number now that I need to really calculate. And also, it's in factored form. And factored form is brilliant. It's awesome. It makes things a whole lot easier. If you can keep it in factored form, by all means do, for as long as you possibly can. If I did it this way, it still works, but I'm really, banking on the fact that I can calculate this. Especially if I'm on the exam and my calculator doesn't work, batteries go out or something. Maybe batteries not included, I don't know. But anyways, we do find the value here in the very end. We get our value of 4. So sine is going to be 4 over 5. Same thing here. I got to find cosine. 13 squared, hit it with the Pythagorean theorem. 5 squared plus b squared. Okay. I can take the 13. I can say, 169. I can say 25 and move some things around. But again, once these numbers start getting bigger and bigger and bigger, it's going to be more and more challenging to do so, especially in your mind. Okay, so a good mental math trick is to use identities, make the difference of squares, apply the identity. This is going to get you a value of 18. What's that going to get you? Okay, and you got to take the square root, and again, we are in quadrant 1, so we are going to be taking the principal square root due to the restrictions right here. Okay, so we'll have the square root of 8, which is going to be 2 root 2. The square root of 18. 18 is going to be 2 times 9. Square root of 9 is going to be 3. You're left with root 2. And a root 2 times a root 2. It's almost like a bad joke. But, you get 2. So we're going to have 2, 3, 2, 4 times 3. Okay, get you 12. So again, it's just another way of how you can go through the calculations. And this might be a really good approach, especially if I don't have these nice, perfect squares that keep popping up. It's really easy for me to come over here now and instead of saying 13, what if I called it 11? Okay. Now it's a lot more challenging. But again, how do you solve challenging problems? How do you learn how to solve them? Look at easier problems and find the echo of truth. You see how it resonates forth. Okay, anyways, enough of that. 12 over 13. Take it, replace it. Hey, look at that. 5 and 13. 5 and 13, the denominators are the same again. I wonder why the denominators keep becoming the exact same every single time. It couldn't be because the hypotenuse for this is the same as this, and the one for that is the same for this. Yeah. So you found a great way to self-check yourself, didn't you? A good observation. When you work through these problems, your denominators better be the same. Otherwise, you get some problems. You need to go back and actually check your problem. Okay, anyways, 48, 65, 15, 65. Take everything, you want to start adding them together. And again, the denominators are going to be identical. So yeah, 48. In the way that I do things, again, I look for patterns, trying to find things a little easier. 15 is going to be nothing more than 2 plus 13, correct? And if I say 2 plus 13, then I can connect up a 2 and 48 very quickly, gives me a 50, which makes calculations a little bit easier to do mentally, which tells me then I'm just adding numbers to, multiples of 10. Makes things very, very easy. 63 over 65. Okay. Again, you can just crunch this out and you can say, okay, 15 plus 48. You can do things just like this, but it'll take you a little bit more time. So if you can find things, make things easier, hey, by all means, go for it. So for these kind of problems, when you're looking for cosine of theta and cosine of phi, you're looking at the summation, step 1. Just come up here to the identity. Write it out just like we did. Step 2, update by what you know. You know these two quantities, take them, plug them in. The next step, look for what you need. You want to get the sine of theta, you're going to need this part right there to figure it out. And how do you figure it out? It goes back to this. Construct your triangle, use the Pythagorean theorem, and then figure out what the value is going to be. Likewise for the other piece. And then just simplify it in the very end, put it all together. What if you take theta and suppose it is phi? Okay, apply the identity. Right here, you're going to have sine, and it's not going to make a lot of sense to look at the difference, but if I looked at the addition, that's going to give us a lot more information. Okay, so I have sine of theta plus phi, which is going to be theta. Take everything, drop it in. You have sine of theta, cosine of theta, plus sine of theta plus cosine of theta. You have two of them. Simplify it and call it 2 sine cosine theta. Double angle identity. This thing's golden. This identity is very, very useful. And since it's so very useful, do you think it might be a good idea to know this identity? Yep, I think so. And a lot of times you're not going to say theta plus theta. You're simply going to say 2 theta. Okay, likewise, if I have cosine 2 theta, that just means, again, that these two are the same. Take it, replace it, drop it in. You will be left with cosine squared theta minus sine squared theta. Okay, it's very, very close to the Pythagorean theorem. Sine squared plus cosine squared of theta is 1. But you know what we can do a little bit more? I can actually apply the Pythagorean theorem. The Pythagorean theorem is a very, very useful theorem. And I can take maybe the cosine and just chunk it to the other side. Or I can do the other way. I can take maybe the sine and throw that to the other side. And what I have when I do things like this is it gives me a way to convert from sine squareds into cosine squareds. So that everywhere that I see a sine squared up here, I could take it and I could replace it with 1 minus cosine squared. Okay. In a very similar way, if I go back to the identity where I have cosine squared theta minus sine squared theta, I can take the cosine, I know what it is, I can replace it with this identity just like that and drop that in. And if I shuffle some terms around and take the negative and distribute, I'm left with 2 cosine squared theta minus 1. And over here, I'm left with 1 minus. How many sine squareds do I have? 2 of them. So yes, cosine 2 theta does equal cosine squared minus sine squared. But guys, it also equals 2 cosine squared theta minus 1 minus 2 sine squared theta. And those two additional identities, they're also really, really important. So for the sine, you have one up here you really got to know. But for the cosine, you have 3 different variants of this. Now, a lot of things start turning very, very quickly. If I was to look at cosine 2 theta, this could be expressed as 2 cosine squared theta minus 1. I could take the 1, I can move it to the other side, and then I can divide both sides by 2. I can move some things around here as well. We'll have sine squared theta 1 minus cosine 2 theta over 2. And these all came from the double angle identities. These two identities, these are very, very important. You're going to find them in the textbook, but they're going to go a little bit further in the textbook. In the textbook, what they're going to do is take the square root. They're going to do things like this. Just remember, plus or minus. And they might even do some other things as well as take this angle, and they'll say theta here and theta over 2 there. And it's commonly known as the half angle identity. We're not going to really go that far with it, but you can get it if you keep pushing on this. We're going to stop right up here. These two identities, these are really, really good to know if you're going on the calculus. Okay, these identities, I commonly refer to these as power reducing identities, because look at the power. It's squared. Look at the power here. It's not squared. And if you can take something from squared to not squared, to the first power, it reduces the complexity down of a problem, which makes it a lot easier to navigate through. Okay. Here's what we have thus far that you're going to have to need to know. Again, you got to know the relationships between sine, cosine, tangent, all the different 6 trigonometric functions, relationships with the ratios of the sides of the triangle. You got to know the Pythagorean theorems, all 3 different variants. You have to know angle sum, angle difference for cosine and sine. And we're not quite done with these yet. There's some more that we're going to churn out here pretty soon. You have to know the double angle for sine, the 3 different double angle identities for cosine. And then this right here, what we're calling the power reduction identities for cosine squared and also for sine squared. And they're very easy to remember. They're pretty much exactly the same. 1 and a 2 and a cosine 2 theta. But what's the difference? Here's your sine. Oh, that's bad. No, it's good. Or was it a sin? I don't know. Okay, you guys have a great day. I'll see you next time.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.